In this video, we are going to lay the foundation for drawing resonance structures. A resonance structure involves moving of electrons, but here are some of the can'ts. You can't move sigma or single bonds, you can't move atoms, you can't increase or decrease the number of electrons, can't change the net charge, and you can't exceed an octet for period 2 elements. We're going to talk about each of these as we give an example of 1,3-pentadiene. For 1,3-pentadiene, I have shown the electrons that can move in red. I will take this second double bond, I'm going to point it coming from the double bond and pointing it onto this upper carbon here. The way we would redraw this, I'm going to put in this double bond again. We'd have a lone pair up here. Now, an important thing to note is that wherever the arrow is coming from, the atom at that end is going to be gaining a positive charge. The atom at the pointy end of the arrow is going to be gaining a negative charge. And we'll see why that is here in a second as we look at our structural formula. In this structural formula, you see that the carbon here has a total of 3 bonds and 2 electrons in lone pairs. Normally, carbon likes to be in control of 4 electrons. So it has a 4 mole charge of the 4 valence electrons minus 3 bonds minus 2 in lone pairs. That gives it a -1 charge. Whereas this carbon down here, he only has 3 bonds and no lone pairs. So he has a positive charge. We're not going to do this for every single one, but just watch how this works over here on the right. And notice that the arrows always lend a negative to the point and a positive to where they came from. So for this next one, where we can draw an arrow, we can take this double bond and again, put it on top of that carbon. We'll draw in the old lone pair that we had last time, and we'll draw the new lone pair. Again, it's going to be negative. We're going to leave a positive at the far end. So you can see that just as before, where it came from, we are missing the last pair of electrons here, and this one has extra, so again, positive, negative. If we then draw an arrow from this lone pair down towards the positive, we will be making what's at the end, the back end of the arrow more positive, so this will become neutral, and this next one down here will become more not negative, also making it neutral. Now we may want to do something similar with this lone pair, bringing it down right here, just as we did before. There is a problem with that, and I will show that to you. We need to follow this rule that whatever is over here becomes more negative, and this guy here is still positive, but we would wonder why. And that's why we look at our structure here on the right. If we put a double bond here, we have forgotten that we have 3 hydrogens here, and that makes a total of 5 bonds for the carbon, which cannot work. That is, this bottom rule here can't exceed octet for period 2 elements. Carbon can only have 4 bonds. And so at that point, you may wish, oh, well, this carbon over here is missing a hydrogen. I wish I could just drag it over there. But we can't do that. You can't move sigma, can't move atoms. We can't change that. We can't get rid of this double bond and just make it disappear. That would decrease our number of electrons. So this is something that we can't do. So we will leave it at the previous structure. Now, a question may be, what do all these resonance structures mean? All of these resonance structures together average out to form what the real structure truly is. They don't resonate, as the name suggests, back and forth quickly between all of these structures. It was once believed, but we have found that to be inaccurate. But when we say average, mathematically, we think all contribute equally. However, in all reality, some contribute more than others. Let's take a closer look at those rules. These rules are in order of importance. The octet rule is the most important, and that question is, do each of your atoms have a full octet? If we look at this first structure here, each of the carbons has their full octet. So we'll put a big check mark. On this next one, we see we have a carbon here that only has 6 electrons. This next one, we have a carbon here and a carbon here that only have 6 electrons each. On the last one, again, we have a carbocation, only 6 electrons. From this, we see that we have a winner. This is the biggest contributor. If we want to continue to rank each of these, we can move on to the second rule. We want whichever one has the least amount of formal charge. We can continue to look at the first one, even though we know it's the best. We look and we go, okay, this one has no formal charge. We'll put a 0. On this next one, we have a formal charge here and a formal charge here. That is 2. On this next one, we have 1, 2, 3, 4. And on the last one, we have 1, 2. That gives us a tie between these, so that's not going to help us much, but we do know that this one is the last. So we will give that one a 4. Now between these two, let's look at the next rule. Number 3 states that the negative must be on the most electronegative atom. However, all of the atoms with negatives on them are carbons. None is more electronegative than another, so that rule is not going to help us. Rule number 4 states that we want to have the most substituted carbocation. So if we look at the second and the last one, we will see that this carbon here is attached to 1 carbon, 2 carbon, and a hydrogen. Carbons are the things that support a carbocation. So this one has 2 supporting it, and this one down here has 2 hydrogens. Those aren't going to help it, and it has 1 carbon. So this is not very substituted. It has 1 substitution. This is disubstituted. So this one on the top is going to be our second place, and this one on the bottom will be our third place. For some of these other rules, let's use another structure to help us give an example. If we wanted this to show another resonance form, we will take one of the lone pairs and move them down onto this single bond to make a double bond. And we will take one of these from the triple bond and place it on the carbon. We can see that the charge on the nitrogen remained the same as it received electrons and lost them. However, the thing that is now negative is this carbon over here. If we go through this biggest contributor rules, first the octet rule. Everything has its octet. Everything has 8 electrons. Next, formal charges. They both have 2 each. So those first 2 rules don't help us. The next one is we want the negative on the most electronegative atom. This negative here is on oxygen in this one and on carbon over here. The more electronegative atom is oxygen, so this would be our biggest contributor. If we were to draw a resonance, we can get this double bond to move here towards the positive. Between these two structures, we have a carbon that is tri-substituted. It has a carbon here, here, and here connected to the carbocation. This one is disubstituted. It has 1, 2 carbons attached to the carbocation. So this second structure would be the most substituted carbocation and would be the biggest contributor.